Right, these are the solutions to the kinematics question. So first off, are, as always, are the definitions and also the symbols as well, because you're given the majority, 95% of the formula, but a lot of exam boards do not tell you what the symbols mean. So S means displacement, that's really important. A and T should be straightforward, acceleration time, and then V is final and U is initial velocity. The distinction between a scalar and vector quantity is very, very important. And then these definitions, which we mentioned in the previous lesson, hopefully you know all this information from GCSE, but really, really important. And these tend to be the easy marks in questions. So the definition of velocity. If you say speed in a certain direction or something like that, that will not get you any marks. They are looking for a very precise set of words, the definition. So the rate of change of displacement per unit time, and also acceleration, the rate of change of velocity per unit time. So you can see the similarity there. And then also what the gradients mean. So the gradient of a displacement time graph is the velocity. The gradient of a velocity time graph is the acceleration. And then, as we said, the area underneath the VT graph is the displacement because S equals V times T. So these are the fundamental ideas that you must be very, very comfortable with in order to understand motion and kinematics. So this question 2, this would be a very easy question at A level. This is more of a GCSE standard. So we've got a few questions about this VT relationship shown. So the acceleration from O to A, that's just the gradient. So you could just work out the gradient if you wanted to. Alternatively, you could use A equals V minus U over T, same thing. So it's 5, take away 0, divided by 2, will give you 2.5. Always write the units, so meters per second squared, ms to the minus 2. Part B, the change in displacement. So it's basically how far has it travelled. And as we said, that's very often the same as the distance, but not always. Sometimes it's totally different. But in this case, distance and displacement would be the same thing. So how far has it travelled between O and A? So we know that that is the area underneath the line. So we have a triangle here. So we want to find half times base times height. So half multiplied by 2 multiplied by 5 will give you 5 meters. Part C, the acceleration from B to C. So important here that we include the negative sign. If you miss that out, you would probably lose a mark. If it asks for the deceleration, obviously you can just write 5. So the V and the U, we need to get these the right way around. So the final velocity right at the end is 0. So V is 0. The initial velocity, U, is 5. So we have 0 minus 5, which gives us this negative 5. So that minus comes out in the maths. So we have a larger value of deceleration than we did for the acceleration. The total change of displacement, so how far have we travelled? Be careful, very often students confuse this with a displacement time graph and say that it's 0 because it looks like we've gone back to the start. Well, that might be true if this was displacement, but it's velocity. So we haven't changed direction at any point. We're always going forwards. We've just accelerated and then constant velocity and then decelerated to stationary, but we're still moving forwards all the time. Either way, we need to find the area underneath this, these 3 sets of lines. So usually students would find the area of the triangle, well, we've done that bit already, the area of the second triangle and the area of the rectangle and add the 3 together. That is absolutely fine, you can do that. A quicker way of doing this is using the trapezium rule, or the area of a trapezium. So it's half times A plus B, or the base plus the top bit here. So we've got 8 at the bottom and we've got 5 at the top. So it's basically the average of those two. 8 plus 5 divided by 2. And then we multiply by the height, which is 5. So you get 32.5. If you would rather divide this into 2 triangles and a rectangle, that's absolutely fine. But it is quicker to work out the area of a trapezium. Right, part E is really important. Very often students think, right, if I work out the velocity for this bit and this bit and this bit, the 3 different velocities, well, that doesn't make any sense anyway because they're changing, and then try to find the average of the 3. That wouldn't work for several reasons, mainly because the velocity is changing in the first and the final section, but also even if it weren't, then the times are not the same. So to add the 3 together and divide by 3 doesn't make any sense at all. That will not work. If we do know the total distance travelled, which is 32.5, and we know the total time. Well, that is one way of thinking about the average velocity. It's the total distance or displacement divided by the total time. Also, if you're struggling in an exam and you're not sure how to do a particular question, always look back at previous parts and think, can I use any one of my previous answers in this final question here? And very often that is the case. Okay, question 3. So you could get something like this in the exam. Again, this is mainly GCSE level really, but it's fairly similar to question 2. So this is where you have to draw or sketch a velocity time graph given the information. So we're told constant acceleration, so that's very important. It's going to be a straight line, constant gradient. After 10 seconds, we've reached 25 meters per second, so that's our first line there. And then we have constant velocity for a further 15 seconds, so 5, 10, 15. And then we have uniform deceleration until we come to rest, which means zero velocity. So we're going to draw that line from 25 to 0, and that takes 40 seconds. So we end at 40 seconds. So that's part A. So part B and C, very similar to previously. Find the acceleration O to A. Well, we can do that in a couple of ways. We could work out the gradient, or we could use V minus U over T. 25 minus 0 divided by 10 will give you 2.5 ms to the minus 2, very important. And then part B, fairly similar. I think my A, B's and C's are slightly confused here. This should be B, C and D. So the next part is find the gradient here. Again, V minus U over T would work. So 0 is our final velocity. Take away 25, the initial velocity divided by 15. That minus sign is important. Also think about significant figures. So this will come on your calculator as 1.6 recurring. So don't write 1.6666 and don't write just 1.6. We have to round this to, in this case, 2 significant figures would seem appropriate. So the 6 becomes a 7. And then the total distance or displacement, again, we could work out the 3 areas and add the 3 together. What I've done is worked out the area of a trapezium. So the base is 40, the top is 15. We're finding the average of those two and then multiplying by the height or the distance between them, and we should get 687.5. That's 4 significant figures. It's probably fine. You could argue it should only be 2 significant figures because that's the number we have in the original data, but 3 or 4 significant figures should be fine for the exam. Okay, the final question. This is thinking about how we represent slightly complex scenarios or journeys with a velocity time graph. Let's have a look at the first one, part A. An object moves at constant velocity, well that's straightforward, and then immediately reverses its direction. So it changes its direction. So we now have negative velocity, that's important. It says with twice the speed or twice the magnitude of velocity. So there's no numbers on here, but we can see that approximately the magnitude of the velocity down here is double the original velocity and returns to the start point. Now this is very important. So even though there's no numbers on here, the approximate sizes of each of these areas should be the same. Well, they should be exactly the same because that represents the distance traveled. So this is where displacement is very important. So we have positive displacement here, and over here we have negative displacement. So if we add those two together, then we have 0 displacement. So we're back at the start point. So that's quite important. Final one, part B, let's have a look. An object is thrown vertically upwards and moves freely until it returns to its start position. Okay. Very often, again, students get confused with displacement time graphs and draw maybe a side view of a parabola, which is the kind of the height that increases then decreases. Totally incorrect. We're thinking about velocity. So initially the velocity is maximum value, we assume positive. It will decrease to 0 at the highest point, and then it will change direction and it will fall back downwards towards the ground. So we now have negative velocity. So this gradient should be the same. The gradient will be the value of g, or negative 9.81 meters per second squared. And that does not change. That's a really important point. Gravity, g, is always 9.81, never changes. The velocity changes, but the gradient, that is the rate of change of velocity, always stays the same. Once again, if we're ignoring air resistance, although I'm not sure that'll make a difference here anyway. The areas of these two triangles should be the same. So the area of the first triangle represents the height that it's on its way up, and the area of the second one should be the same because it's obviously going to rise to the same height that it falls.